first interactive session. Okay. As noted, this boot camp is going to place a large emphasis on interactive use of the software. And within this first session, we're going to be not building a model from scratch, as we will for many of the sessions, but instead working with a model. And in order to work with that model, we're going to be drawing on some of the resources that I mentioned in my last lecture. So specifically, if you were to follow this URL over here, this ABM Bootcamp 2018 materials, you will find within that folder that's presented to you a folder that is called Models Built-in Class. If you click on that, there's a preview for exploration, and I'd like you to click on that. Okay. Within that, there are subfolders for providing, for each day, a set of the models that we're going to be building that day. And those will give you a glimpse of where we're going. I'd like you to click on day one, and you'll notice there are two models. That may not be obvious that they're models, they just have names. But they finish with the extension .alp, which indicates there are any logic projects. Okay. Now, one of them is called GIS and PA Environment version 5. Okay, that's a model that depicts a food environment and a physical activity environment within a GIS space. Now, I'd like to sort of teach you how to make use of these models to get them onto your computer in as easy a way as possible. The ideal way is to right-click on that. I think on a Mac it's what, Option click or something? Control click. Okay. Control click. And you should be able to choose download. Okay. I'm sorry? So right click. Now, there's another way too, which I'll show you, which some of you may end up in inadvertently. And it's good to know this trick as well. So who needs help? TAs stand ready for deployment. A phalanx is forming in the back. Okay? Who needs help? Who needs help? Okay? Okay, another way is this is more scary, but sometimes you get to it anyway, and it's good to know how to get out of it and resolve the issue. If you were to double click on that, you'll see something kind of scary. Well, for some of you it might be intriguing, but you'll see this. If you go up to the upper right, if you end up in this situation where you're showing this puzzling stuff, if you go to the upper right, there should be a download icon, this little down arrow with the bar beneath it, and you can press that as well, and that will download it. And then you can press escape, and it will bring you back there. So in short, the preferred way to deal with these, and this will apply to models shared this way and models shared in the 100 plus models I've shared with you as examples. This is the way you download them. You either right-click and say download, or you double-click and select download up here. Either way, you want to get that model onto your computer. Okay? So who would like help with that? Okay? Front row, sector 1. Yeah. Okay, now, anyone else? Help? Help? The TAs stand ready. A formidable force. Okay. Okay, so once it's on your computer, I'd like you to, if you haven't already done so, to open it with AnyLogic. That may require you to start AnyLogic. Now, I'm going to start AnyLogic along with you to show you something that may trouble you. So I'm starting AnyLogic 8.1.0. Like you, I'll switch over to 8.3.2 this afternoon. when AnyLogic first comes up, it will come up in a variety of configurations. The one you're most likely to see on your part would be something that looks like this, okay? So it shows some information about getting started, some tutorials which are recommended. You can go open some examples. If you get to this point, what you're actually going to want to do is to, if it puts a message here, you can just say close. You'll want to minimize this, okay? And it should allow you to then see a screen that looks something like this, including a menu up here. So how did I do that? Well, I'll show it to you again. If it comes up like this, you just use this little minimize bar up here to get back to AnyLogic, okay? Who needs TA help? The TA stands stalwart. Some of them sit stalwart as well. Okay. Okay, ladies and gentlemen, once you have that, I'd like you to file open, and I'd like you to navigate to the place to which that downloaded. So when you downloaded it, it was placed in your downloads folder, very likely. And you're going to want to go to that location, whither it went, and you're going to want to open it, okay? So if it went to downloads, you want to go to downloads to open it up. Now, this is a matter we'll go through many times in the course of the boot camp, so it's worth sweating this detail. If you need help with this, just to get it all down pat, just grab a TA here, okay? Okay, who would like a TA? Who would like a TA? Okay, great. So if you go click on this, you can open up this model. And it's going to open it up in a way that will show you some information about the model. Were you people able to open the model? Okay, I see cranial inflection suggesting yes. Who would like TA help? Okay. TAs are ready. Does anyone need a bit of help? Okay, I sense Aiden is, as always, an exemplary in the service. Okay. Who else needs help? Okay. So, ladies and gentlemen, what you'll see here should be on the left-hand side elements within the model. It's what's called a model hierarchy. It basically shows what's inside the model. And we'll come to learn about what each element of this means. For example, down here in the X's are experiments. These are scenarios you can run with the model. The models we're building in this boot camp are dynamic models. They're models that are designed to be simulated over time. They depict a situation that evolves over time. And experiments run scenarios with the model that make different assumptions with the model. So, for example, one might assume a small population, one might assume a larger population or a medium one. Some might assume physical activity is enabled in the model, others might assume they're not. So those X's are going to be experiments. The things above, with the kind of Da Vincian logo in red, the measure of man, those will actually indicate things called agents, okay? And agents will describe types of entities in the model. Person, for example, or a supermarket, or a park, or a convenience store, which will have characteristics and will often evolve itself over time. And finally, there's something called main, which is kind of the global environment, the global situation, the overall context for the model. And that's in main here. So you should see that. Does everyone see this here? Okay. Now, you might also see something opened called main. Do you see that? Yeah? Okay. So main depicts a map. It depicts a map of a famous city in the world. Does anyone recognize it? Some of our colleagues from down under might.
Melbourne?
Yes, it's Melbourne. It's Melbourne, Australia. Okay. You'll also note that beyond the map, there's a set of information presented above that right now will be a buzzing, blooming confusion, but it consists of some graphs and some what are called parameters that will encode assumptions. But in order to give you a feel for what's going on in the model, I'd like to run it. Okay, I'd like to try running it now. I'd like to run it in a way that will clue you into a common technique we'll use. So I'd like you to click on the experiment called Big Population, and I'd like you to right click on it and click Run. That's one way you can do this. There's another way too, which you can do it with this this little drop down up here. But I would suggest right clicking and choosing Run, or on a Mac, Option Control click. Okay, someday I'll learn the 3-fingered swipe and all that sort of stuff. Okay. So ladies and gentlemen, if you do that, a window should come up. Do you see that? Do you see a window come up here? So how did I get to there? I right-clicked on this and I chose Run. There's several other ways. I could have said Model Run, and it would ask me which thing do I want to run, and I say, well, I want to run the Big Population. Or I could have used it with this choice here. In general, AnyLogic provides a couple different ways of undertaking tasks. Tries to make it convenient to you to allow you to choose the way. The one I find most helpful is the one that's most specific. I just right-click on the one I want to run, and I choose Run. Okay? So if you get to a window, now this window is meant to actually allow me to be more specific, to change assumptions, and to control how quickly the simulation is going to run. I'm just going to say Run here, okay? And something you should see is an environment here. Now, you'll notice that down at the bottom, there's an indication of time, and time is in fact going on. It's continuing apace. And next to that, next to running, is actually a little down, it looks like a bit of movement. And that's to indicate that actually AnyLogic is communicating with a server. It's communicating with GIS information to figure out the routes that people take. Okay, so what we're actually simulating is behavior over time within this model, and you'll note there's a date associated with it, November 12, 2015, and time is continuing on throughout it. Now, we're not running this at maximum speed. If you were to run it at maximum speed, it would speed it up a bit, but even so, because we're dealing with a large population, it needs to figure out the routes that people are taking. It's going to be going at a slower pace for the next little bit. But within this model, yes?
So where, maybe you mentioned it during that first bit of news, but where is this data actually coming from?
It's a good question. It is coming from in a couple places. So in this case, we have some assumptions, which I'll be walking you through in the model in just a minute, okay? And there's some data associated with those. Data associated with, for example, the impact of physical activity on weight, or data related to how the presence of a convenience store nearby affects people's shopping habits. There's some of it that's captured in the model. In addition to that, within this model, there's a great deal of data being used from a geographic information system, which is actually located over the web. It's actually going and finding information about the routes between people's homes and grocery stores that are in fact at certain locations within Melbourne. And it's through figuring out those routes, it's saying, okay, the shortest route from A to B is from, say, a home to a store is this, and it will then use that information to route through it. Similarly, the location of parts, that's also coming from this geographic information server for Melbourne, Australia.
So if you're tracking people, are you tracking them through Google? You're tracking them through Waze? Like, where's that?
Oh, no. Good question. So this model includes a set of characteristics which are specified in a fixed way. They're called exogenous. That would have to do with the location of supermarkets, the location of parts, the location of homes. Within this, the location of supermarkets and parts and convenience stores. That's according to existing GIS databases, the types of databases that would be used by a system like ArcGIS. By contrast, people's home locations and the number of people within those homes, that information is generated by the model. So we're positing, okay, people live within an area in an evenly distributed fashion. We're not going into the details of this particular person is in fact a specific person in real life. Rather, this is a synthetic population being generated. A population of representative people, as it were, that may have some diversity as we'll see in their weight or diversity in their preferences, but they're being placed into this environment in a fashion that's not in fact based on the true location of homes or specific identities of people in the world, but rather is model generated. So we have this mixture here of combination between a model generated information and information that's drawn from GIS databases. And I'll show you in a minute how we get that model generated synthetic database, okay, of people. So you'll notice that in the experiments for this model, some positive medium populations, some larger, some smaller, but the point is that for those populations, what we're creating is different synthetic population sizes. It's synthetic in the sense that the people aren't truly representative of a particular person. Now, in fact, on the final day of the boot camp, we will talk a fair bit about use of these models with big data. And some of our research, which some may be familiar with, is focused on leveraging technologies, for example, like smartphones, to in fact, with people's consent, understand their patterns of movement, patterns of behavior. And Winchell back there in the corner has spent a fair bit of time building models, for example, which articulate with that data. Ivan here, also in the back, has done similarly. And so it is possible to have models that incorporate real-world patterns in data where people's meanderings in the model are in fact reflective of empirically collected data about people's movements as gathered through wearables or smartphone devices. And we'll talk on Friday about ways that those two can come together in concrete ways, whether it's mobility or networks, people's preferences. Models can provide of this sort can provide a very effective way to knit together data from large-scale data sources. And if there's interest before that, I'd be glad to talk about it. But this is a synthetic population imposed on a map, which is in fact empirically grounded, if that's helpful. Yeah. So, ladies and gentlemen, what we see here is a model running over time, and over time, you'll notice people moving around. There's particular homes, which are shown here in blue. There's convenience stores, which are shown in green, the sort of box store. And there's supermarkets, which are shown in this larger size. The locations of each of those is based, in fact, on empirical data for the city of Melbourne. And people, in fact, if you were to slow this down and look, they're in fact moving along routes, streets or bike paths, depending on the settings for the model, which allow them to travel from one of these locations to the other, to engage in food-seeking behavior. They may go to a supermarket and purchase a larger larder of food, which they then use for a number of days before going back. In other cases, they go to a convenience store for a quick milk and bread run, and they come back, or they come back with what is that? What are some of the things in Australian convenience stores again? I forgot. Floaties? Is it?
Meat pie, yeah.
Meat pies. What is it? Tim Tams. Okay. I'll take your word for it. And so we have people engaged in food-seeking behavior and Tim Tam seeking behavior here, as well as going to supermarkets. Now, if you were to pull down at the top here, some of you may wish to zoom in here. You can do so by pulling down this and checking the view option. You probably see something like that right now. You check view, and that would allow you to zoom in to the map. Right-clicking will allow you to drag the map along those lines. But if you actually go in and were to scroll down this navigation menu, scroll down to where it says population. It requires a fair bit of scrolling, but it's alphabetical. You could see population. What you'll find is a depiction of some logic. Logic associated with food seeking, with decision making, with behavior, with, in fact, physiological change on the parts of individuals. So, for example, we'll see here an individual depicted who has a certain home, who has a certain preference for Tim Tams, and who has a certain weight at a given time. We can, in fact, click on this, view a weight trajectory. We'll see that their weight is oscillating here in kilograms as they eat larger quantities of meat pies and Tim Tams. And there's some energy expenditure posited through resting metabolic processes and some physical activity-related energy expenditure. Over time, they're engaged in food-seeking behavior. Under some cases, they'll head to a supermarket, and others head to a convenience store. They'll engage in shopping, and in fact, that engagement will refresh their larders of supermarket meals that they have in their home or in their convenience store meals. You'll notice that this is an individual who is actually getting more supermarket meals than convenience store meals. They've by more than a factor of 10 to 1. Despite having a fair preference for convenience store meals. That may be because they're close to a supermarket. It makes it very convenient. Associated with each meal, there's a decision-making process. Do they have only convenience store food available? If so, they'll eat that. If not, do they have supermarket food? If so, they'll eat that. And if they have both types of food, they'll flip a coin according to their preferences. So here we're depicting a sort of logic associated with an individual. The individual has a certain status. They have a certain weight over time. They have a count of meals associated with them of different types. So heads of lettuce from the supermarket and other healthy fare, and then floaties and Tim Tams and meat pies from the convenience store. But at the same time, that status is evolving over time. That weight is changing. And as the weight is changing, their health Based on that, their classification, for example, in terms of weight categories could change. And similarly, the number of meals to which they have recourse over time changes. This is a particular individual, and if we were to scroll here among different individuals, we'd find individuals differ. This is an individual who's a bit heavier, with a weight of 80 kilos. Some individuals are lighter. And we could scroll among the different members of the population in a way that reflects their diversity. So what we have here, ladies and gentlemen, is a synthetic population where each person in this population is engaged in behavior. They're engaged in food seeking, they're engaged in eating behavior, they're engaged in behavior associated with their weight change, associated with their food consumption. If we were to scroll back up here, we see the model as a whole. And I'd like you to draw your attention if we scroll up here some more. I've chosen the right click. You can see people now the model is proceeding very quickly. That's for a technical reason. It's figured out the requisite routes that a person is likely to take. It's gotten the requisite information. So now it's simply running forward. And if you scroll up, what you'll notice is that beyond depicting particular individuals, what we have is summaries across this population. So we have these individuals within the population who are shown here on the map. Each of whom has certain characteristics and are evolving over time. But above this, we can summarize behavior associated with individuals across the population. So for example, here we have a scatter plot. Each dot represents a person. On the x-axis is the fraction of the meals they've eaten at the convenience store, and the y-axis is their weight in kilograms. And you'll notice that there's an association between those. So we have, for example, individuals who engage in larger amounts of convenience store food seeking tend to have higher weight, although there is some variability. Further up, we'll find depictions which, for example, compare the distance to a grocery store in meters to their weight in kilograms. Here, associations may be present, but they're less obvious. There doesn't seem to be a very, very clear linear association, certainly. Further up, grocery store to convenience store distance ratio. How much closer are they to a grocery store than to a convenience store? Here, you'll find this is the ratio on the x-axis and their weight on the y-axis. If the grocery store is much further away than a convenience store, they'll tend to be a somewhat higher weight. And then finally, further up, the preference for the meals versus their weight in kilograms, and then their distance to parks versus weight in kilograms. Now, this particular scenario, I did not posit any specific behavior associated with parks. I didn't actually characterize the park use by individuals. Here, we're running this model in a way that is blinded to the physical activity benefits of parks, and we're seeing the results that come from that. The results summarized across the population. Again, each person is a dot. This is the distance to the nearest park, and this is their weight in kilograms. And there's no obvious relation, no obvious big relation here. I'd like to stop this model now. We can stop it by this big button up here. We could also simply close it up there. And I'd like to now run the model that's called run the scenario that's called big population with walks. This is the same scenario, except now we're enabling the effects of physical activity. We're reflecting the fact that people's physical activity is stimulated by the presence of parks, and we're going to ask, how does that affect the types of outputs we see? How does it affect the outcomes in terms of these relationships, say, between food seeking, food preferences, and weight. Because now we don't just have one thing affecting weight trajectories in the form of food. We have now a diversity of distances from parks that's also shaping people's physical activity and, by extension, their weight. So I'm going to run this. How did I do that? I'll rehearse it again. What I did is I right-clicked on big population with walks. You'll notice, maybe I'll just comment here. Earlier I ran big population, and notice it said physical activity on here. Big population with walks has that checked. Big population, what we ran before, did not have that checked. So big population with walks, I'm going to run this. So here we're simulating the effects of physical activity, associated with parks. I'm going to expand this here, and I'm going to run this as fast as possible. That's that button here. So here we see the same basic environment. I'm going to enlarge it here just so we can make it out a little bit more clearly. But you'll notice that there are parks in the vicinity, and this model is actually going to characterize the impacts of those parks on physical activity. So here's the first graph. I don't know if you remember what that looked like before, but it was a much narrower linear relationship. Now what we're getting is actually a relationship that's still there, but it's less tight in its form. I'm just going to go up to the two topmost graphs here, which are perhaps most instructive. So this is distance to the nearest park versus weight. Here you see a more clear relationship. So the further the distance from the park, the higher the weight seems to be. There's sort of a lower bound on their weight here, but a fair diversity above that. That was quite different from what we saw before, where the distance to the park was somewhat immaterial to their weight. So we ran a scenario where we said, okay, parks are not going to, we posit no impact of parks on weight. Here we're running a scenario where we do simulate the impacts of parks on physical activity and therefore weight, and we notice the associations generated. Now, why am I dealing with these associations? Because, ladies and gentlemen, when we're dealing with data from the world, it's often in the form of associations. Folks are very familiar with this, right? Countless papers within the health sphere focus on associations observed from the data between factors. What we have here is associations coming from this model. But the associations are arising from the model, are being generated by the model. Where are these associations coming from? Yeah.
Sorry, buddy.
Sure.
But all your scales are different, all your axes are different to ours.
Oh,
When you look at that, so how do you change the axes? Obviously.
I don't know what I did.
that's interesting. So are we sure we're looking at the same graph? This is the second to largest one, second to highest one. This is the furthest one up. Okay.
They're auto-scaling, aren't they?
They are auto-scaling, but it should be within the same rough range. Are they very different ranges? Okay. I'd like to look at that later. I can't.
Two of us is different. Or three of us are different.
Three are. Okay. So who else is different? Okay. So and we're sure we're looking at the same graph, right? Let's say the topmost graph. Is that? Yeah. Okay. And your scale on the x-axis is what?
It's all 0 to 1. Our scales are all 0 to 1.
Fascinating, and it's not the graph just down, which is 0 to 1.
No.
Okay. Okay, we have had a situation where, due to different localization settings, it's shown, time is shown differently or something, but this wouldn't bear on that.
Oh, right, we're all looking at the wrong
It wasn't
interface.
view of the model itself, not the ROM.
Oh, okay. I'm sorry. Yeah. This is a view of the running model. These associations are generated by the running model. Yeah, and whereas you're probably looking at this sort of thing, which is a fair, I can understand the confusion. So what's going on here? The model is depicting, so this is the model. This is sort of how the model is set up to display things. This is the results of the model. But the deeper point here, ladies and gentlemen, this is a very important point. The model that we're seeking to explore here is describing an underlying process of interactions. It's a process that involves individuals. We explored those earlier. We saw, if we drilled down, we have populations of people, for example, each of whom is in different situations. There's a process described here by the model for how that person evolves over time, how their weight evolves, how their food-seeking behavior evolves, how their decision-making takes place with regards to what they're going to eat. And that process plays out over time and leads their weight to change in a certain fashion. Their larder of available sets of food to change over time. Each individual is placed in a context. They're placed in a geographic context by which they're circulating, for example, here in the city of Melbourne, and interacting with resources. But that evolution described by the model, that evolution of the person at an individual level, their interaction with the environment, gives rise to results which are emergent. They're implied by the model, but they're not immediately obvious just looking at the model. And some examples of those implied results are shown here. For example, the relationship between the fraction of the meals they eat at convenience stores or their weight in kilograms, or further up, their preference for meals versus their weight for convenience store meals, or the distance from parks and their weight in kilogram. These patterns result from the model. The model is giving rise to them. The assumptions that we've specified to the model generate these patterns. Each individual here is shown as a dot, and they evolve over time in their state. But what's going on is that we have in the patterns generated associations that are captured. Now, these patterns might be then subsequently compared with empirical data. We might have data from a study, for example, that's looked at the relationship of a person's distance of their home from a park and compared that with their weight, right? And we could compare this model's results along these lines, its predictions, its generated behavior to that empirical data, and we could use it to challenge the model, or we might recognize the model's picking up with its simplified view of some of the processes taking place. It's in fact picking up important features of what we see in empirical data. In short, a model captures assumptions in it, but it generates patterns that can then be compared, scrutinized against, critiqued based on empirical data, and can help explain sometimes empirical data. So these patterns that we see here are generated by the model. they're entailed by the model assumptions, but they're not immediately obvious when you look at the model. They're the result of a lot of things coming together. For example, this preference for meals from convenience stores versus weight needs to contend with the fact that individuals engage in physical activity dependent on their park distance, and the distance to parks might have some association with the distance to convenience stores or grocery stores. And as a result, we get generated patterns from the model, emergent patterns from the model that are not at all obvious when you first look at the model assumptions. If we were to stop this and look at the model assumptions here, look at how we describe a person as evolving over time, and look at their environment in terms of the city of Melbourne, it's not at all obvious what those patterns will be. We use a model to generate the logical consequences of these assumptions, amongst other things, so we can test whether those logical consequences implied by a model are consistent with empirical evidence. In short, does what's implied by the model in terms of empirical patterns jive with what we know from the world? To what degree does it help explain what we know from the world? To what degree does it help us understand patterns we see in the world? So this is one use of models, and this is a model that combines many types of data from GIS servers on park location, convenience store, and supermarket locations, with information related to individual food-seeking, physical activity, and weight change. So that's a glimpse of a model. You'll also notice that this model is fairly visual. This is not an accident. It's not a curious feature of the situation. Models, ladies and gentlemen, capture theories. They capture dynamic hypotheses about the world. What we see here is an operationalized theory of how people's behavior takes place with respect to food seeking, weight change, physical activity, and the dependence of parks. This is a theory. It's an operationalized theory. It's a very specific theory, in other words. Operationalized meaning I can actually run it. It's precise enough I can simulate its effects over time. That operationalized theory here is placed in a form that is explicit. A form that is, once you learn this language, fairly transparent. Transparent for critique. Transparent for criticism on the basis of what's known, and therefore transparent for refinement. So the fact that we're putting a stake in the ground, taking a working hypothesis and saying, I posit this type of behavior on the part of individuals. This is how people make decisions about their food. This is how people make their food-seeking behavior, that the effects of distance to, say, a convenience store versus a grocery store affect people's behavior in this way, that people's weight changes affect them this way. I put a stake in the ground. I say, this is my working hypothesis. I can run it. I can see the implications and test whether they're consistent with the evidence. But more than that, by putting it down in an explicit way, I can help other people understand my assumptions, understand my hypothesis, and critique it. In short, models, by making these assumptions explicit, making them precise, help us in two ways to refine our thinking. Number one, by making it patent, by putting it out there in explicit fashion, they allow other people to see our thinking and to say, well, I disagree with you about this fashion. That's a virtue. If it's trapped in our heads, if we have this whole theory in our heads, we're not going to be able to get it critiqued as readily as if we put it out there. Is this theory correct? No. It's almost certainly got some major flaws. But the model, but modeling it out will help us identify those flaws more quickly. It'll help us arrive at effective critiques that will advance our understanding more quickly. That's one big advantage. But the other advantage is because it's operationalized, we can run it and we can see the patterns that come from it. And we can compare that with evidence. And by comparing with evidence, we may find that the model sounds all good. It may be consistent with our evidence and the evidence of our colleagues, but when we run it, it just ain't consistent with our empirical data that we observe. It ain't consistent with what we know from studies. And there too, we've taken a step forward. We've advanced our understanding, because if we couldn't run our theory in this way, if we couldn't state it, put a stake in the ground, articulate our theory and run it, and see the results, we wouldn't have realized there's this latent inconsistency between what we think is the case and what actually is. We might have a very beautiful theory that it's this certain way, but it just ain't so. Because when we run it, we find that the logical implications of this, those patterns we saw of the association between distance to a park and people's weight, or distance to a convenience store, people's weight, or preference for convenience store meals and people's weight, that those patterns just don't jive with empirical data. So in short, models like this provide us a way to advance our understanding more quickly, more deeply, and more reliably than if we just carried around our theories in our heads. If we carried around our thinking in kind of an inchoate way that we couldn't test in the crucible of empirical evidence, test against our colleagues' understanding by putting it out there in the clear light of day. So this is a model. This is a dynamic model. Why is it dynamic? Because we posit some underlying situation and it evolves over time. It evolves as time passes, people's location changes. They engage in food-seeking behavior, their weight changes, their larder changes, the number of convenience store meals that they have change. It's dynamic. It changes over time. And a dynamic model generates behavior over time based on its specification. We specify certain rules, certain actions within the model in addition to its state, and we let it run, and it produces behavior over time that's sometimes surprising. Those graphs that we saw, are they implied by this? Yeah, in some sense they're logically implied. Did we pre-specify them? Not directly. We specified things that might logically imply them, but they were generated by a complex interaction of factors here. And without running the model, what's implied by the model is often not obvious. Even a very simple model often yields non-obvious results. Yes?
We have fresh coffee and tea out there if anybody would like some.
Awesome. Thank you, Christine. Okay, so that's a first glimpse of a dynamic model. A lot going on there, a buzzing, blooming confusion. But it gives you some point of reference here about where we're going. We're going to be building a fair number of these models. We're going to build a large part of this model on Wednesday. You're going to see how you put it together, how you specify it. Some of you may prefer to hear case studies for some of the more advanced parts. Some of you may want to actually build all these different pieces up step by step in a way that would let you see these pieces. I haven't shown you all things. Some of you may want to explore this model more. I'll give you a hint. If you click on places, you can add supermarkets to certain locations. And you can see how adding to the density of supermarkets changes people's weights over time, for example. But we'll leave that for a later time. I think we'll break now. We'll partake of the beverages and the food out there, and we'll reconvene in 10 minutes to take a look at this issue of dynamic models from a more conceptual basis that will provide a bit of sort of concepts to underlie some of the buzzing, glooming confusion you've seen. Okay? Thanks very much.